So we're going to end this section on applications to physics and engineering by showing a surprising connection between centroids and the volumes of solids of revolutions. The following theorem is called the Theorem of Pappus, and it says, let R be a plane region that lies entirely on one side of a line L in the plane. If R is rotated about that line L, then the volume of the resulting solid is the product of the area A of region R and the distance d traveled by the centroid of the region R. So we're going to do a quick proof of this theorem. And we're going to say let R be the region bounded by y equals f of x, y equals g of x equals a, and x equals b. We will rotate about the y-axis and use the shell method. So I've gone ahead and I've drawn the region R that's being described, and we are rotating about the y-axis, and we want to use the shell method. So our volume here is equal to 2 pi times the integral from a to b of the radius times the height of our shell. So I'm just going to draw a shell. The width of that shell is delta x. I know that the radius of this shell is the distance from the axis of rotation to the shell. So that's our radius, and that is x. And then the height of our shell is f of x minus g of x. So we have x times f of x minus g of x, and then we have dx. Now, if we ignore the 2 pi and we look at the definite integral, that should actually look pretty familiar. Here is where it should look familiar from. Here are the formulas for x bar and y bar, the x coordinate and the y coordinate for the centroid of a region R. And if you look at the formula for x bar, it looks very similar to the integral that we just took a look at. The difference is that if I take this equation and I multiply both sides by a, then these will cancel out. And so the definite integral that we were previously looking at is equal to a times x bar. So we have that the volume is equal to 2 pi times x bar times a. And if I reorder this, this is the same thing as a times the quantity 2 pi x bar. Now, we have the area, which is what we're looking for because we want the product of the area of the region R and the distance d traveled by the centroid. So what I'm going to do is I'm going to draw my centroid. I'm going to estimate that it's about right there. And the ordered pair for this centroid is x bar comma y bar. And if I took the centroid and I rotated that about the y-axis, then the distance it would have traveled would be the circumference of a circle because it's traveling in a circular path. And the circumference that it would be traveling is 2 pi times the radius. And in this case, the radius is x bar. That's the radius. So we can take this and we could write this as a times d, where d represents the distance traveled by the centroid. And that concludes our proof. Example 7 says use the theorem of Pappus to find the volume of a sphere of radius r. Let's approach this by drawing a semicircle on the xy plane. This ordered pair is going to be negative r comma 0. This one's going to be r comma 0. And then the highest point on our semicircle will be 0 comma r. And if we wanted to get a sphere out of this, we would take the region bounded by the semicircle on the x-axis and rotate it about the x-axis, and that would give us a sphere. Now, if I want to think about the centroid of this half-circle region, I know something about the centroid without doing any calculation. Because our semicircle is symmetric about the y-axis by the symmetry principle, we know that the centroid lies on the y-axis. And because our semicircle has more mass on the bottom, it would be below the halfway mark between 0 and r. So I'm just going to estimate that our centroid is about right there. And I'm going to label this x bar comma y bar, which is equal to 0 comma, and then I don't know what the y bar value is, but we could solve for that. So before we do that, we want to calculate the area of the semicircle. And so the area is equal to 1/2 pi r squared, since we know the area of a full circle is pi r squared. And then now that we have the formula for our area, we can use this to help us with y bar now. And if you don't remember, the formula for y bar is 1 over a times the integral from a to b of 1/2 times, in this case we could just use f of x quantity squared, because our lower function in this case is the x-axis. So before we move forward, I should probably figure out what the function is that we're looking at. So I know that the equation for a circle is x squared plus y squared equals r squared. If I solve this for y, I would get plus or minus the square root of r squared minus x squared, but because we're only looking at the upper half of the circle, I could just rewrite it as y equals the square root of r squared minus x squared. And here I want to take the reciprocal of the area that we found previously, so I'm going to take the reciprocal of this, and that's going to give me 2 over pi r squared. And our limits of integration are from negative r to positive r. I'm also going to factor out the 1/2, and then we are squaring our function, which is the square root of r squared minus x squared. So let's do some simplification. These 2's will divide out, and I have 1 over pi r squared. I also have that after I've squared our integrand, we're left with r squared minus x squared dx. And r squared minus x squared in terms of x is symmetric about the y-axis, so we can learn symmetry principles that we learned earlier on in this class, and so I can make my lower limit of integration 0. I would just need to multiply my output by 2, and that's going to make things slightly easier for us with a lower limit of integration being 0. Now, when we're integrating this, be careful because we're integrating with respect to x. Why am I bringing that up? Because I will often have students do something like, oh, I have an r there, and the antiderivative of r would be r cubed over 3. However, we're not integrating with respect to r, we're integrating with respect to x, and r is a constant in this scenario, so the antiderivative would be r squared times x minus x cubed over 3, evaluated from x equals 0 to x equals r. So let's go ahead and plug in our limits of integration. On the outside we have 2 over pi r squared, and then if I plug in r for x, we're going to get r cubed minus r cubed over 3. And if we plug in 0, that's just going to become 0, so I'll just close off that bracket. Then we have 2 over pi r squared times finding a common denominator, and then simplifying will give us 2r cubed over 3. And then multiplying these and simplifying, we're going to get 4r over 3 pi. And then from here, if we wanted to calculate the distance traveled by the centroid, that would be equal to 2 pi times y bar, which is the value that we just found. So 2 pi times 4r over 3 pi. And that is equal to 8r over 3. And then finally, using the theorem of Pappus, we find that the volume of the sphere is the area of the region times the distance traveled by the centroid. So the area of the region, or the semicircle, is 1/2 pi r squared, and then we are multiplying this by the distance traveled that we just found. And when we simplify this, we end up getting 4/3 pi r cubed, and that should not be surprising because earlier on in this class, we derived the volume of a sphere in the section on volumes of solids of revolutions using the disk method. So that completes this video.